Dive Logic and Suzi look beneath the surface of every ocean, lake, and river to discover a world of constant communication. Whales sing across thousands of miles. Submarines exchange encrypted signals. Scientists track climate change through acoustic sensors. Yet for most of human history, communicating underwater has been one of the greatest technological challenges we have ever faced. Water is not simply a barrier to sound as we know it on land. It is an entirely different medium, one that bends, absorbs, and distorts signals in ways that have puzzled engineers and researchers for generations. The story of underwater communication is not just about physics. It is about survival, exploration, national security, and now, the dawn of artificial intelligence reshaping everything we thought we knew about how sound moves through the deep. To understand why underwater communication is so complex, you first need to understand how sound behaves beneath the surface. On land, sound travels through air at roughly 343 meters per second. Underwater, that speed jumps dramatically to approximately 1,480 meters per second, more than 4 times faster. This happens because water is far denser than air, and sound waves transfer energy more efficiently through tightly packed molecules. However, speed alone does not tell the whole story. Sound underwater does not travel in a straight line. It bends, bounces, and refracts depending on 3 critical variables: temperature, salinity, and pressure. Near the surface, warmer water slows sound down slightly. As you descend deeper, the water gets colder, and sound slows further. But go deep enough, and the increasing pressure actually speeds sound back up again. This creates what scientists call the sound fixing and ranging channel, commonly known as the SOFAR channel. It sits at a depth of roughly 1,000 meters in most oceans and acts like a natural acoustic highway. Sound waves that enter this channel get trapped and guided horizontally across enormous distances with minimal energy loss. The United States Navy discovered this phenomenon during World War II and used it to help locate downed pilots by having them detonate small explosive charges that could be heard thousands of miles away. The SOFAR channel remains one of the most remarkable natural phenomena in acoustic science. But while nature provides this convenient highway, the ocean is also filled with noise. Biological sounds from marine life, ship engines, underwater earthquakes, and even rainfall create a constant acoustic background that makes clean communication extraordinarily difficult. Every signal you send underwater must compete with this chaotic environment, and that is where the real engineering challenge begins. Traditional underwater communication relies primarily on acoustic modems, devices that convert digital data into sound waves and transmit them through water. Unlike radio waves, which are absorbed almost instantly by seawater, sound waves can travel significant distances, making acoustics the dominant technology for underwater data transfer. However, acoustic communication comes with serious limitations. Bandwidth is extremely narrow compared to what we enjoy on land. Where a standard home internet connection might deliver hundreds of megabits per second, underwater acoustic systems typically manage only a few kilobits per second over long distances. Latency is also a major problem. Because sound travels relatively slowly compared to light, there is a noticeable delay in every transmission, which becomes increasingly problematic as distances grow. Optical communication using blue-green laser light offers much higher data rates, but only works over very short distances, typically less than 100 meters. Because water absorbs and scatters light rapidly, researchers have also explored radio frequency communication at extremely low frequencies, which can penetrate seawater to some degree. But these systems require enormous antennas and offer extremely limited data rates. The result is that underwater communication has historically been slow, unreliable, and expensive. Submarines must surface or use trailing antennas to communicate effectively. Underwater drones lose contact with operators in complex environments. Deep-sea research stations struggle to transmit data in real time. These limitations have driven decades of research, and now artificial intelligence is beginning to offer solutions that were previously unimaginable. Artificial intelligence is not simply improving underwater communication. It is fundamentally reimagining what is possible. The ocean is an unpredictable environment, and the acoustic channel through which signals travel changes constantly based on currents, temperature shifts, marine life activity, and human-generated noise. Traditional communication systems use fixed protocols that struggle to adapt to these dynamic conditions. Artificial intelligence changes this by enabling systems that learn, predict, and adapt in real time. Machine learning algorithms can now analyze the acoustic environment continuously and adjust transmission parameters on the fly. If a signal is being distorted by a thermal layer, the system can automatically shift frequencies, change encoding strategies, or reroute the signal through a different path. This kind of dynamic adaptation was simply not possible with conventional rule-based systems. Deep learning models trained on vast datasets of underwater acoustic recordings are becoming remarkably good at separating meaningful signals from background noise. Where a human engineer might struggle to extract a clean data stream from a noisy ocean environment, a neural network can identify patterns and reconstruct signals with impressive accuracy. This has enormous implications for everything from submarine communications to deep-sea environmental monitoring. Artificial intelligence is also enabling a new generation of autonomous underwater vehicles to communicate more effectively with each other and with surface stations. These vehicles, sometimes called autonomous underwater vehicles, can now form intelligent networks where each unit shares information about its acoustic environment, helping the entire swarm optimize its communication strategy collectively. This cooperative approach dramatically improves reliability and range compared to single-unit systems. Beyond communication itself, artificial intelligence is helping researchers decode the acoustic signals produced by marine life, particularly cetaceans such as dolphins and whales. Projects like Project Padi, which stands for Cetacean Translation Initiative, are using machine learning to analyze sperm whale clicks, known as codas, in an attempt to understand their communication structure. While we are still far from a full translation, the progress being made is extraordinary and could eventually help us understand one of the most sophisticated natural communication systems on the planet. The practical applications of advanced underwater communication are vast and growing rapidly. In the military domain, navies around the world are investing heavily in systems that allow submarines to communicate securely without surfacing, reducing their vulnerability to detection. Artificial intelligence-driven acoustic systems can now encrypt and transmit data in ways that are far harder for adversaries to intercept or jam. In the commercial sector, offshore oil and gas platforms rely on underwater communication networks to monitor pipelines, control remotely operated vehicles, and ensure worker safety. As these operations move into deeper and more remote waters, the demand for reliable high-bandwidth underwater communication grows accordingly. Climate science is another area where underwater communication technology is proving transformative. Networks of autonomous sensors deployed across ocean basins can now transmit real-time data about temperature, salinity, carbon dioxide levels, and ocean currents. This data is critical for understanding climate change and improving weather prediction models. The ability to collect and transmit this information continuously and reliably is directly dependent on advances in underwater acoustic communication. Looking further ahead, researchers are exploring quantum communication underwater, using entangled photons to create theoretically unhackable communication channels. While still largely experimental, early tests have shown that quantum signals can survive short distances in water, opening a fascinating new frontier. There is also growing interest in hybrid communication networks that combine acoustic, optical, and radio frequency technologies, switching intelligently between them based on conditions, with artificial intelligence managing the entire system dynamically. The ocean covers more than 70% of our planet's surface, yet it remains one of the least connected and least understood environments on Earth. As artificial intelligence continues to mature and our understanding of underwater acoustics deepens, we are moving closer to a future where the deep ocean is as connected as the surface world. The implications for science, security, commerce, and our relationship with the natural world are profound. What began as a wartime necessity has evolved into one of the most exciting frontiers in modern technology, and the deepest chapters of this story are only just beginning to be written. Dive into another episode of Dive Logic coming soon.